Hello students, welcome to the lecture series by Center for Distance and Online Education, Bharati Vidyapeeth, deemed to be University Pune. I am Dr. Suvarna Patil. I am the facilitator for the subject Operating System for BCA course. So let's start. In the last video, we have seen the basics of memory management. The remaining part is covered in this video. We start with virtual memory. The virtual memory concept was devised in 1961. What is done in virtual memory? The size of the program, if it exceeds the size of the memory, the operating system keeps that part of program currently in use in the main memory and the rest is on the disk. So it means the size of the program, though it exceeds the size of the memory, still the operating system keeps that part of the program which is currently in use and in the memory, and the rest of the part which is not required, which is currently not in use, will be kept on the disk. This concept can be used in the multi-programming environment to effectively achieve the more degree of multi-programming. Now, the virtual memory is just a concept. This concept can be implemented by using a technique of either paging or segmentation. In the coming part, we'll see how the paging and segmentation is done. We start with paging. Now, program generated addresses are called as a virtual address and it forms a virtual address space. Now, what is done in paging? The virtual address space is divided into pages and the physical memory is divided into frame. That is called as a page frame. Now here pages and page frame, they are of having exactly same size. We have a page table that maps the virtual page into physical memory page frame. If the related page frame exists in the memory, physical address will be found and there will be no page fault. But if the related page frame does not exist in the memory, in that case the page fault will occur. That means the related page does not exist in the memory, it is on the disk. The memory management unit, it will map the virtual address into the physical address by using the page table. In case of page fault, the operating system loads the required page into the physical memory by swapping and mapping the process and updating the page table. So when the page is again loaded in the memory, accordingly the page table will be updated. This diagram shows you how virtual address space is divided into number of pages and how the physical memory space is divided into frame, that is called as a page frame, and how the particular page is loaded in the frame. Now page table, what is the task of page table? The main aim of page table is to map the virtual address into physical memory address. Now when the CPU generates a virtual address, it is in the form of like a decimal number. So when the decimal number 8196 is generated by CPU, it is finally converted as a physical address as 24580. Here the virtual address is converted into binary format. It's a 16-bit binary number. Now virtual address, it is divided into two parts: virtual page number, higher order bits, and the offset, which is a lower order bits. The virtual page number, it acts as an index into the page table where we'll find the entry for that virtual page. Now next to index in page table, the page frame number exists. The page frame number, it will replace the virtual page number, and then the offset is attached to the lower order end. Here you can see with the help of diagram how this virtual address is converted into this physical address. 8196 converted to the binary format, 16-bit number. These 4 bits will be an entry point to the page table. Now it is 0010 means 2. Now with this entry we can see we get a physical address as 110. The next column is for present absent bit. If it is 1, the page is present. If it is 0, page is not present. So with this 2 entry, we got the physical address 110. It is copied here as first bit, and this offset remaining 16 bit will be remaining 12 bits will be copied as it is here. So finally you get this outgoing physical address. Now here, if memory size is large, the page size is small, then the page table contains many entries, lakhs of entries, and that will result in wastage of memory to store the page table. As the page table is large, lot of time will be required to map the logical address into physical address. So this is the task and function of a page table. Let's see the advantages and disadvantages of paging system. Paging is very easy to implement. It is using a technique of swapping. So swapping is very easy due to the same size of virtual page as well as the page frame. Now here disadvantages: page table needs a large memory to store as a page table, which may not be good with a system having a small amount of memory. So if page table size grows and if it is very huge, very large, then more amount of memory will be required to store the page table. There is one more concept next to the paging, that is demand paging. Now in this technique, the process resides in a secondary memory. They are loaded in the memory only on demand, not in advance. So the pages which are currently required by the process will be in the main memory. Now this will help to increase the degree of multitasking, and the pages which are not required by currently executing process will be on the secondary storage device. Next we'll see the page replacement algorithm. Now when the required page is not exist in the memory at that time, the page fault will occur, and the OS will select a page which will be out of the memory, and the new page will be loaded in the memory. So when the page required is not available, at that time the page fault will occur. Now when page fault will occur, the operating system will choose a page to be swapped out of the memory to create a rule. Now the question is, which page is to be swapped out of the memory to create a rule? That selection of a page when the page fault will occur will be dependent on the page replacement algorithm. So in the next part we'll discuss all these algorithms with its merits and demerits. The first is optimal page replacement algorithm. The algorithm says that replace the page which will not be used. So it is based on the knowledge of the future usage of a page. The algorithm is easy to describe, but it is difficult to implement. Now, the page with higher number is removed. Suppose we have a first page which is not used for 10,000 instructions, and we have a second page which is not used for 7,000 instructions. In this case, higher number is with first page. So here the first page is removed when the page fault will occur. So this algorithm requires a future usage of the page. The next algorithm is not recently used page replacement algorithm. Here the operating system keeps track of each page. Each page will keep 2 bits. So 2 bits are related with each page. One bit is for M, other is R. So M is for modified and R is for reference. So it is having a page table entry for each page. These 2 bits are used to design this algorithm. Initially, both the bits are set to 0. Means the pages are not referenced, they are not modified. Now on each page fault, the operating system checks M and R bit of all the pages. And now the pages is divided into these 4 categories. Like class 0 is for the page is not referenced, not modified. Class 1 not referenced but modified. Class 2 page is referenced but not modified. And class 3 the page is referenced as well as modified. So here the operating system first removes the page from class 0. So the page is not referenced as well as it is not modified. Whenever page fault will occur, the OS will select a page from class 0, then class 1 and then it will go on. So here according to this category, the page will be replaced. The next algorithm is first in, first out page replacement. Here the operating system maintains a list of all pages currently loaded in memory. Now on each page fault, the page at the end is removed. So page at the head of the list is the oldest page and the page at the tail is the recently arrived page. So it works according to the first in, first out criteria. The new page is added at the end of the list. The major problem with this algorithm is to remove the page which is heavily used that came early. So the page has come early but it is heavily used. But still according to this algorithm that page will be replaced. So it is first in, first out algorithm. The next is second chance page replacement algorithm. So it's an enhancement of FIFO algorithm. Here the second chance is given to the page which is referenced in the past instead of throwing it out of the memory. In this algorithm, after each page fault, this algorithm checks the R bit of the oldest page which is at the head. If that R bit, if it is 0, the page is replaced, and if that bit is set to 1, the bit will be cleared and the page is put at the end of the list. So here we are giving a second chance to the page instead of throwing it out of the memory. So here the algorithm moves the pages around the list, which may be the time consuming mechanism. You can see the page loaded here first and the pages which are most recently loaded are added here. So when the A is selected for after the page fault, it will be again added at the end and it is treated as a newly loaded page. So one more chance is given to the page. The next is clock page replacement algorithm. In this case, OS maintains a circular list in the form of a clock. So here the pages are form the clock shape. They are maintained in a circular list in the form of a clock. Here the hand points at the oldest page. Now, after each page fault, the page which is pointed by the hand, it is checked. If the R bit is 0, then the page is removed from the memory and new page is loaded at its place. After that, the hand will be moved one position ahead. If this R bit is 0, then it is cleared and the pointer is moved to the next page. So here the R bit will decide which page to be replaced, which page is getting evicted. So if R is 0, evict the page. If R is 1, clear R and then advance the hand. This is about clock page replacement. The next is least recently used page replacement algorithm. This algorithm says that remove the page which has not been used for longest time when the page fault occurs. Now here LRU is implemented in the hardware in this case. LRU using matrix when the pages are referenced in the order 0, 1, 2, 3, 2, 1, 0 and 3, 2, 3. So in this order the pages are referenced and this matrix shows the condition, the situation when the pages are referred in this order. Now when the page frame K is referenced, OS will set all the bits of that row to 1 and then all bits of that column are set to 0. You can see here when the page 0 is referenced, all the bits in the row are set to 1 and then all the bits in the column are set to 0. So it is giving value 0, 1, 1, 0, 1, 1. When the page 1 is referenced, we will set all the bits in the row to 1 and all the bits in column to 0. So we can see here 0, 0, 1, 1 the value of first page and 1, 0, 1, 1 the value of the page number 1. Now at any time the row with the lowest binary value is the LRU page in the matrix, J binary value of the page frame. Now here you can see page 0 is having value as 4, the frame page 1 is having value as 0, page frame 2 is having value as 12 and page frame 3 is having value as 13. Now in this case, as the row 1, the page frame 1 contains the lowest binary value, so page 1 is the LRU page and it will be replaced when the page fault will occur. So page frame with the lowest value will be replaced in case of LRU. This is the implementation of LRU using an hardware. The next is not frequently used page replacement algorithm. Here we'll see it's a version of LRU, how LRU is implemented in the software. So in this algorithm, each page has its own software counter which is initialized to 0. Now you can see the diagram. There are 5 clock tick. Clock tick 0, clock tick 1, 2, 3, 4. Now after each clock tick, the operating system scans all the pages in the memory. After that, R bit value of each page will be examination and R bit value is added to the left of the counter and then counter moves 1 bit to the right. So when page fault occurs, the page with lowest counter will be removed here. You can see the diagram. In the final diagram, you can see if there is a case of page fault and page to be replaced, the page number 3 is having the lowest value. So that will be replaced in this case. So here this algorithm does not forget the number of count, means if the page is heavily used, in the past, but recently it is not used at all. Still, it is thrown out of the memory. So here every page will maintain a counter, and that counter will help to remove the page from the memory. Until now, we have discussed about the concept of paging. So to implement virtual memory concept, we have two techniques, paging and segmentation. In this slide, we'll discuss about the segmentation. A paging system, it provides a large linear address space, but it can face the problem with the growing table because one table may bump into another. We can see in the diagram, we have different memory area for symbol table, source table, constant table, we have a pass tree, and we have a call stack. So what is happening here? The source table, it will contain the printed listing. The symbol table, it contains the names and attributes of variable. The constant table, it contains the integer and floating point constant. The pass tree, it contains the syntactic analysis of the program, and the stack used for procedure calls within the compiler. Now here all these four tables will grow dynamically, and if there is no free space available, they will bump into each other. Now this is the problem of paging. Now segmentation is a solution to the above mentioned problem. Let's see what is segmentation. Now in segmentation, it provides many completely independent address spaces with variable sizes that grow or shrink independently without affecting other segments. So here the memory will be divided into multiple independent address spaces. Here we have total 5 segments. We have divided the memory into 5 segments. Each segment is of variable size. We can see here segment 0, 1, 2, 3, 4. Every segment is having a different size. Segment 0, it requires 20K. Segment 1 is with 12K. We have segment 3 with 16K of memory and segment 4 with 12K of memory. So here the segments can grow or shrink according as per the execution of the process, and it will not affect on the other segment. This is a positive part of the segmentation. Now here every segment address which is generated, it will starts with 0 and that will end to the maximum size of the segment. Each segment address generated will have two parts. One is the segment number and the second part will be the address within the segment. What are the advantages of segmentation? Now, as we have seen, the first biggest advantage is it simplifies the growing and shrinking of the data. So segments can easily grow or shrink. As each segment address starts with 0, a call to procedure in segment n uses two parts. So it will have n, 0. It means starting address of each segment would be 0. And we need to mention which offset, which address you are accessing within the segment. With the help of segmentation, sharing of data among different procedure, it becomes very easy. So sharing of data can be possible with the help of segmentation. Here, as every segment is having a different address space, it has its own memory area, so it will not face a problem of protection. So every segment has a different kind of a protection mechanism, and the memory is having a mechanism for giving a protection for the process. In this diagram, we can see how segmentation is actually implemented. We can see in this diagram A, B, C, D, E. It shows the snapshot of the memory at given time. We can see we have 5 segments here, segment 0, 1, 2, 3, 4, and the process is loaded in that particular segment, and some of this memory is occupied by these processes. Now in the case B, in the diagram B, we can see there is some unused memory area. This is empty memory area. So what is happening? The process which is loaded at segment 1, it has now exited, it has completed the execution, so it is out of the memory. So new process is loaded with the segment 7. Now that process require only 5K of memory. So 3K of memory is unused here. After some time, you observe the figure number C. The process loaded at segment 4 will leave the memory and new process will come at this segment 5. It requires only 4K of memory. So here 3K of memory is again empty, it is unused. After some time in the diagram D, we can see the process loaded at segment 3 will go, segment 6 is there, and again 4K memory is free. So here this much area is free, this 4K is again free, 3K of the memory is again free. Now if new process comes and it requires some 6K of the memory, we can't assign the process because the area is not contiguous. So what can be done? The operating system executes an technique, it uses a technique called as a compaction. So what it will do? It will move all the whole on one side and all the processes on the other side. So here the problem of segmentation is external fragmentation. It is solved by using a technique of compaction. Using compaction, all the holes will be moved on one side of the memory and the processes are moved on the other side of the memory. The compaction technique, it takes some resources as well as it is time consuming, but it solves the problem of external fragmentation. So this is the end of unit storage management. Thank you.